Hello again. In this video, I'm going to go over the definition of the derivative of a function at a point. So the derivative of f at a is written like this. We put a prime next to the function f, and then it's being evaluated at a. Okay, so this is how we denote the derivative of f evaluated at a. And it's equal to either of the following two limits, provided that they exist. And a is in the domain of f. Okay, so one way you can write the derivative of f evaluated at a is it's equal to the limit of f of x minus f of a divided by x minus a as x approaches a. And this is a typo in the book. This should be x minus a, not x minus 1. Or another way you can write this derivative of f evaluated at a is equal to the limit as h goes to 0 of f evaluated at a plus h minus f evaluated at a divided by h. Now, if this derivative of f evaluated at a, if it exists, then we say f is differentiable at a. You know, not all limits exist. When this limit exists, then f is said to be differentiable at a. Of course, if the limit doesn't exist, which is a possibility, then f is said to be not differentiable at a. Okay, and I just want to look at an example where we use this. So let's look at example 4. So we're given this function, and we're supposed to find the derivative of f evaluated at 2. And remember, when you have a prime here, that means the derivative of f. Okay, so this means the derivative of f evaluated at 2. And then we're going to use the result to find an equation of the line tangent to the graph of f at the point 2, 3. Okay, so let me show you how we can work this out. Okay, so you could use either of the two limits that we talked about to find the derivative of f evaluated at a, and I'm just going to use this one. So we want f prime evaluated at 2, the derivative of f evaluated at 2. Okay, and so that's equal to the limit as x approaches 2 of f of x, which is this function, minus f evaluated at a, so f evaluated at 2, all divided by x minus a, in other words, x minus 2. Okay. Okay, so let's find f evaluated at 2. When you plug a 2 into this function, you get square root of 4 here. Square root of 4 is 2, and then 2 plus 1 is 3, which makes sense because that's this ordered pair, 2, 3. So the f of 2 is 3. Okay. Okay, so now let's just simplify this. This is 2x minus, the square root of 2x minus 2 all over x minus 2. Okay, now one way we can evaluate this limit is to try direct substitution, but notice when you directly substitute 2 in for x, you get 0 over 0, so this is indeterminate. And so we need to do something to make it determinable. And what I'm going to do here to make it determinable is to multiply by the conjugate of this top term And remember, the conjugate would be equal to this term, except one of the terms has a sign change. So I'm going to change the sign in front of the 2. And instead of having a -2, I'm going to make this a +2. Okay, and that's called the conjugate of this. Okay, so we're going to multiply this by the square root of 2x plus 2. And of course, if I multiply the top by this, I have to multiply the bottom by this because it has to equal 1. Otherwise, I change the value of this fraction. Okay, and so let's just FOIL this out. Now, when I multiply these two together, square root of 2x times the square root of 2x just gives you 2x. And then here you get 2 times the square root of 2x. And then notice here, the inner term, you get -2 times the square root of 2x. Okay, and then the last term would be -4. And so notice these terms are going to cancel out. And that's the reason I multiplied by the conjugate. By multiplying by the conjugate, you're forcing the middle term to cancel out because one of them will be a plus and the other one will be a minus. Okay, now on the bottom, I'm not going to FOIL this out. I'm just going to leave it as it is. Okay, and then I'm left with 2x minus 4 on the top. And what I'm going to do is I'm going to factor a 2 out of that, and that's going to leave me with x minus 2. And that's going to cancel with the x minus 2 in the denominator. Now remember, when you're trying to change this into a determinable form, you're hoping to get something to cancel out. And so once I cancel these x minus 2's out, then hopefully it becomes determinable. And it does, because I no longer have 0 over 0 once these cancel out. When I plug a 2 in, I get 2 divided by, when I plug in 2 into the bottom, it looks like I get square root of 4, which is 2. And then I have 2 plus 2, so that's 4. So I get 2 over 4, which is a half. Okay, so that is the derivative of f evaluated at 2. Now, one thing I want you to notice is that this definition right here should be familiar to you if you watched the last video. If you remember in the last video, this limit, we showed that this limit was the same as the slope of the tangent line at x equals a. But now we're calling it the derivative evaluated at a. And so the derivative evaluated at a is the same as the slope of the tangent line evaluated at a, or at a. So this 1/2 is not only the derivative of f evaluated at 2, but it's also equal to the slope of the tangent line at a, and in this case a is 2, which happens to be the location where you're evaluating the derivative at. Okay, and so the second part of this problem, we're supposed to find the tangent line, or the line tangent to the function at the point 2, 3. And we know the slope of the line, the tangent line, at 2, 3 is 1/2. And we know this point, we know the tangent line goes through this point, and so we can use the point slope formula to find the equation of that line, the tangent line. Okay, and so let's just plug everything in. The slope is 1/2, and then the point that it goes through is 2, 3. Okay, so x1 is 2 and y1 is 3. And then we just want to solve for y here. Multiply the 1/2, or distribute the 1/2 here, and you get 1/2 x minus 1. And then I'm going to add 3 to both sides. And so you can see you get 1/2 x, and then you add 3 to both sides, and it becomes a plus 2. Okay, so this is the equation of the tangent line at the point when a is equal to 2. Okay, so then let's just take a look at this graphically. A graph of this function, square root of 2x plus 1, looks like this. And then this is the point 2 comma 3 that we're trying to find the equation of the tangent line at. And you can see that's the tangent line at that point. And it certainly has a positive slope because it's going up. And then the y-intercept should be 2, which it is. And so that seems to be a reasonable answer for the tangent line, right? 1/2 x plus 2. Okay, so one thing that we've learned is that this derivative evaluated at the derivative of f evaluated at a is actually equal to the tangent line, the slope of the tangent line at a. Okay, so just keep that in mind. Later on, in the next section, we'll talk about the derivative as a function of x. Okay, and we'll look at that in the next video. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.